Well, welcome back. We got a test Friday. So we'll do that at 8 o'clock Friday, chapter 3. We've covered everything pretty well. You have a take-home quiz that's due Friday. Maybe I could help you with that. I don't mind helping you a little bit. And I want to give you back your quizzes from the other day, but I think I'll just do that last. Let's start with, do you have questions on this take-home quiz or questions from the book? Or yes, ma'am?
Number 13.
Yes, I was going to say that.
On the take-home quiz?
Right here.
Yeah. Okay. That's probably a pretty good one. I don't mind helping you. You know, it is a take-home quiz. And I told you you could get some help. I also told you to try to get help and not copy things. Now, listen. So I'm about to help you and you're about to copy things. I guess that's okay. You know, I did say I'm randomly grading 4, so in a way, I don't mind helping you with some. I'm gambling a little bit. You know, maybe I'm not helping them that much. But I might randomly pick 15. Who knows? I mean, anyway, I'll help you with a few of these today on here. I may help you exactly, or I may help you with similar stuff. But let's look at 15. 15 says. By the way, did you want to ask me something?
Oh yeah, I didn't get one.
Oh, a take-home quiz? Yeah. Does anybody need a copy of a take-home quiz? Let me see what I got here. Where did I get these? Oh, we missed class Friday, so I posted these on Canvas. So I sent you an email and I posted them under files. So I guess many of you printed them out, but I never did hand them out. But I got a few copies, so I can hand out a few. Yeah. Anybody else need one? I don't know. I think I tried to say this Monday, but maybe I didn't get them out. Okay, so 15. 15 says, the space shuttle Scotlantis, have you heard of that? Launched the other day, and they don't even do space. Space shuttles are retired. An observer named Scott was standing 6,000 feet away. The angle of elevation from Scott to Scotlantis was growing at a constant rate of 0.06 radians per second. Okay, it's one of these pictures, and then I sort of gave you a picture here where this rocket launches. There's a rocket here, and it's launching, and it's going up into space. There's an observer over here, and he's watching it. So he's watching it, and his angle of elevation is growing. So I don't know. I might call this H. This H is growing, and this angle theta is growing. Are you following me? As this launches, that angle. What's not changing is this 6,000 feet right here. That's not changing. So, I don't know. I read the problem and drew this picture. That's step one. I mean, y'all ought to do that. It helps. I mean, you got to start correctly, and that helps. So now I stare at the picture and I try to come up with an equation that relates these variables. I can come up with an equation that relates these variables. The tangent of theta, right, is h over 6,000. Is that okay with you? You know that, don't you? Opposite over adjacent is tangent, right? So that was cool. That was obvious. You know, if I wanted to solve for theta, I mean, I can, you know, in a way I could work with this equation, I suppose. But in another way, I could just solve for theta. How would you solve for theta? No, solve for theta. Well, take the tangent inverse of both sides. So then I would have the tangent inverse of h over 6,000. truth is, you know what, maybe I don't want to solve for theta in this problem. And the truth is, you got an option, you guys. You can work with this, or you can work with this. Or you suggested, hang on, he suggested multiply by 6,000. If I multiply by 6,000, I get this. 6,000 tangent theta equals h. So, you know, here's 3 versions of the same equation, if you don't mind. I mean, I started with the main idea, but I can solve for h or I can solve for theta. And the truth is, I'm going to probably do this derivative with respect to t. I'm going to do an implicit derivative with respect to t. So you can do that in that situation. Oh, that's a 6,000. Thank you. You can do it there, you can do it there, you can do it there. I could take the derivative with respect to t. So all 3 of these work. I don't mean to confuse you. I don't really want to do all 3. Let me read a little more here. What they gave me, let's see how they worded this. The angle of elevation was growing at a constant rate of 0.06 radians per second. What did they just tell me?
The derivative with respect to
d theta dt. No, they told me the angle was growing at a rate of, so they just told me d theta dt. The rate of change of the angle. I have to read the words and realize that's what they'd said. Looking at the units sort of helps too. They did say radians per second, which is angle over time. This is an angle over time. So it was 0.06 radians per second, they said. At what rate is the height of the space shuttle changing? Okay, so what are they asking for? dH dt. Thank you. The rate at which the height is changing. The rate at which the height is changing is dH dt. So that's what they're asking for. That was given. When we do these related rate problems, they often say at the instant, because you know these things are changing. So, but we're trying to find the rate of change at a particular moment during the changing process. So they said at the instant when the angle was 52 degrees. So I think I better write that down somewhere. I'm looking for this at the moment when theta is 52 degrees. But you don't plug this in too darn early. If you plug this in too early, you don't have any variables. Theta is a variable that is changing. We have to leave theta a variable for a while. At some point, I'll plug in 52 degrees for theta, though. At some point, but not too soon. What I really need is to relate these rates. I need to take the derivative implicitly with respect to t. And like I said, I could go with all 3 of these options. Yeah, I really want to do the first one, the very first one, and the reason is because they're asked for dH dt, and I can easily, so I want to go with that top one. So I don't mean to confuse you. There's a lot of different ways to approach this problem as I've outlined here, but I want to take this first problem and I want to take its derivative. You ready? The derivative with respect to t. You ready? You walk into the 6,000, it's a multiplied 6,000, it sits there, and then you do the derivative of tan theta. The derivative of tan theta, secant squared theta. We got that memorized. We got that memorized. The derivative of tan theta is secant squared theta. Now you have to do the derivative of the little theta. That's the little d theta dt. Because we're doing this with respect to t, implicitly with respect to t. So every variable we run into, we do its derivative and then we throw a little d theta dt on it. Or on this side of the equation, I'm going to do the derivative of h. I could call that a 1, but then I'm going to do dH dt. I don't know, you guys, I don't know, I'm going to pause here on this problem, but you know, when I introduced this concept of related rates, that the idea was you take the derivative implicitly with respect to t. So let me just try this one. Take the derivative of the variable a with respect to t. Thank you. You go over here and you take this derivative. You bring the 2 down, 2 pi, that's a constant, and then the r is to the first. But then you have to do dr dt, multiplied on dr dt. On yesterday's quiz, on Monday's quiz, you were supposed to do the volume of a cube. The volume of a cube is, the volume is x cubed. All three sides are x. It's x times, it's length times width times height, but length and width and height are all x times x times x. Can you do this derivative with respect to t? Equals 3x squared dx dt. In that problem on the quiz the other day, they gave me an x, and they gave me a rate of growth of x, and I fill those in and I answer their question. On our ladder problems, our ladder problems, we usually have a Pythagorean theorem set up where we have something like this, and we take the derivative with respect to t. Let me just do this one. How do I do it? 2x dx dt plus 2y dy dt equals 0. I'm doing all, this is what these word problems are, these related rate word problems. I'm doing all these derivatives with respect to t. So I'm in the middle of this problem and I just went off and tried to show you, I don't know, how all these, this is how all these problems work. And so this is just another example of one of those dudes. Yes?
I have a question regarding the v equals x cubed.
Yeah.
Alright, so when you multiply by dx dt,
Yeah.
does that mean that you're trying to solve for x or trying to find the derivative of x? Is that what you're doing?
Well,
Because I'm going to think that that's the chain rule, or that you spit out that dx dt.
right, but why are you asking about this one and not this one? That's because they're all the same.
Okay.
But I don't, it's okay. You can ask about this one, but they're all the same. I mean, the idea is I'm taking the derivative with respect to t.
Gotcha.
So that's the idea. And you look up here and there ain't no damn t's anywhere to be seen.
Right.
So that's kind of the new weird thing. You're taking the derivative to a variable that ain't even there. And so every variable you run into, you have to do its derivative with respect to t. Well, that's how you do it.
Right.
And you're right, the idea is the chain rule, that when you do this derivative with respect to t, first you do the power rule,
Okay.
and then you have to go inside and look at the little x and take its derivative with respect to t. And that's that. You're right. I mean, you're right. I think you said, is that a chain rule you're doing there? And yes, spitting this out on the end was a chain rule. So was sort of this one, I guess. So was this one kind of. You 2x, and then you do the derivative of the little x with respect to t. 2y, and then you do the derivative of the little y with respect to t.
Yeah, because at the beginning, I just don't see how there's a chain rule here when you could have just did.
I know, it's all about that respect to t. I mean, you're right, man.
Yeah.
Listen, if I'm doing this thing, take this derivative with respect to x, please. Take this derivative with respect to x. That's a different, yeah, you could call it dvdx. You could actually just call it v prime or dvdx.
Okay.
But what is it? It's 3x squared and you're done. Because you're doing it with respect to x. Watch this. If you wanted to talk your way into it, you could say, well, okay. He says, now I got to do the chain rule. He told me I got to do the damn chain rule. So now I'm going to do the derivative of that x with respect to x. But with respect to x, the derivative of x with respect to x is
1.
a 1.
Okay.
The derivative of x with respect to t is dx dt.
Okay.
Yeah.
It's all about that, whether that variable jives or not. If that makes any sense. All right. So, I don't know. I'm trying to make these word problems, well, whatever. I'm trying to explain
I think it's clear.
the strategy. The strategy is come up with an equation and take its derivative with respect to t. And there's no t's up there, so this is how you do it. I did several examples. Let's get back to this one. They are looking for dh dt. I got it all by itself. I just got to fill this other stuff in. It turns out the d theta dt was given. That's a little 0.06. This is 6,000. What about the actual theta? The actual theta was given. It was 52 degrees. I'm going to plug in 52 degrees. Try to get the secant of that. Try to square it. Multiply by this. And then also multiply by 0.06. guys okay? That's it. That's the answer. So now, maybe you need help with this. How the hell do you find the secant of 52 degrees? How do you find the secant of 52 degrees? Well, yeah, but you ain't got no secant button.
1 over cosine.
You ain't got no secant button.
1 over cosine.
1 over cosine.
So it's 1 over cosine. You gotta know that. You gotta go
Squared.
1 over the cosine of 52 degrees. After you get that, you better square it. That would be good.
Yeah.
You multiply by 6,000, you multiply by this, and you got it. When you get this answer, though, I believe it's going to be in feet. How do I know it's in feet? Because that 6,000 is in feet. I know I also got some radians in here, but radians are a funny little unit, boy. They come and go as they please. They're kind of a little ghost unit. They're almost unitless because radians are just numbers. I mean, we call them a unit because we try to make them distinctive from degrees. But anyway, whatever this is, it's feet per second.
Okay.
Anybody got an answer?
949.
That's the final.
0.77.
Is that the feet per second?
Yeah.
Okay. Is that what y'all, anybody got?
I got that.
Yeah, good. Okay, I think the problem then asks you to convert it to miles per hour, maybe?
Yeah.
So I might let y'all do that. Okay. So that's the answer, I guess, if we agree. I'm trusting you, though. Do more than 2 people think that's the answer? Okay, more than 2 wins.
I got 13,551.
Yeah, me too.
13,000.
Let's see. So how'd you do that? Did you do the cosine of 52?
Yeah.
Did you reciprocate that?
Square.
And then square it. And then multiply by 6,000.
Yes.
And then multiply by 0.06. Are you in radian mode in your calculator? Or are you in degree mode or radian mode? Because you punched in a 52 degrees, so you better be in degree mode.
I was in degree mode and I got 949.
Yeah, I was in degree mode too, and I got 949. And I was in degrees.
Some radio.
All right, that's your problem. When you ask for the cosine of 52 degrees, you better be in degree mode for that. Yeah, and yeah, that's the problem. Cool, thank you guys. Yes, sir.
I just want clarification on the last part. So if anywhere in your equation there's a degree, then you know to go to degree mode?
Well, look, yeah. This is, right.
Should I say for the purposes of this test?
Well-
If you see a degree?
Well,
No,
right.
fair.
I don't know. Right. I'm going to try to do this without giving you a huge lecture here, but listen, you guys. You know, when you have trig functions, you're plugging in angles. They can be in radians or in degrees. When you plug in an angle, it can be in radians or in degrees. When you spit out the answer is just a number. So the answer isn't radians or degrees. The input for the angle is radians or degrees. The answer is just some number, 0.234, 0.765. I mean, the answer is just a number. So if you're inputting an angle that's in degrees, your calculator should be in degree mode. If you're inputting an angle that's in radians, your calculator should be in radian mode. And how do you know, maybe? If somebody says, evaluate this when x is 10, do you see a little degree on that? All right, then they're asking for you to evaluate this when x is 10 radians. If they say x is 10 degrees, then they're saying, please evaluate this. Now you know it's degrees. But either way, yeah.
Thank you.
Okay. What else, you guys?
Can we do number 7?
Number 7.
Yeah, it's, yeah, I see it.
Yeah, Yeah, 7's pretty nasty. You're right. I don't mind help. I'll help you with 7. You ready? 7's just a terrible, nasty, implicit derivative problem. It's y e to the 2x. I don't mean to use words like terrible and nasty. I don't know why I do that. I'm sorry.
It is. It's just ugly.
Oh, you agree. I know, but it really is math, so it's really beautiful.
Right.
I mean, you just can't get away from it. You can pretend it's, oh, this is terrible and nasty. It's all pretend, because the truth is it's beautiful.
All in the eye of the beholder.
Well, I know. And, right. So I'm saying, oh my God. All right, I walk into this, and I want to do its derivative with respect to x. It's called find the derivative with respect to x. It's called, well, actually just says find the derivative. We know what the derivative is. The derivative is dy dx, or y prime. But because it's all mixed up, this is definitely an implicit problem. And here I go. When I walk into this, it's a product rule. So here I go. How do you take the derivative of y with respect to x? dy dx. Times, write the other dude down, plus, write down the y, and take the derivative of the other dude. Okay, so the other dude is an e to the 2x. How do you do the derivative of e to the 2x? E to the 2x times 2. Good job. The derivative of an e function is just himself, but the chain rule says you got to do the derivative of the little 2x. That's what spit out the 2. But overall, that was a product rule right there. Hey, guess what? Here comes another product rule. Here's another product rule. You ready? So derivative of the x is just a 1. With respect to x, it's just a 1. Write down the other guy. Plus, write down the x. And now let's take the derivative of e to the y. The derivative of e to the y is just himself. But the chain rule says you have to do the derivative of the little y. The derivative of the little y is dy dx. So that is like a chain rule, spitting that out there. Yes. Cool, so that was a little product rule right there. That was a product rule. Equals the other side. Uh-oh, guess what? The other side's a product rule. That's a little teeny baby product rule here. In the world of implicit differentiation, that's a product rule. And here we go. The derivative of the x, multiply by the y, plus, write down the x, and take the derivative of y. Whew, that was fun. Now, do I have to do more? I mean, I do. You do. But I could stop here. I mean, the rest of this is algebra. We have done the derivative. Where is the derivative? It's the dy dx. It shows up here, it shows up here, and it shows up here. If you want to solve for it and get it by itself, which you're supposed to do, I would move all the terms with the dy dx over to one side, move all the terms without the dy dx over to the other side. Then all these terms on this side have a dy dx, so what do? Factor it out and divide by all that crap you right. Can you see that happening? Is that a good enough explanation, or do I have to do it? I'll do it. All right, so I'm leaving this dude on this side. Oh, by the way, I'm going to do it. Okay. All right, I'll do it. But I will, as I do it, I'm going to do a couple moves at once. So what did I say? Move all the dy dx dudes over here. And then I'm going to factor out a dy dx. So I'm going to do all that at once, if you don't mind. So I move. He's already over here. I factored a dy dx out of him. He's already over here. I factored a dy dx out of him. Are you with me?
Yeah.
These two guys? They're over here, and I factored a dy dx. Look, who else is coming over here? This guy's coming over here. When he comes over here and I factor the dy dx out of him, what's left?
Minus X.
A negative x. So now all the dy dx's are over here. I factored out the dy dx. Remember, I'm moving everybody else to the other side. That y is already on the other side. Who else is going to the other side? This thing here? Let's move him to the other side. Who else is going over there? This guy here? Move him over there. That's what he is. So I moved those over. I moved the dy dx's over here. I factored out the dy dx, and now to solve for it, you divide by that junk. So it's kind of a similar, the algebraic steps are always kind of the same here on these problems. To solve for dy dx, this is kind of the strategy. So you got it. Dy dx is this over this. There's nothing to simplify. It's just a big, terrible, nasty, beautiful implicit differentiation problem. Yes?
Can you do 11, please?
11.
Yes.
Yeah, 11's a lot easier than it looks, maybe.
I feel like it's just not done that.
Yeah, it is. It's good. It's easy. Hey, can I talk about the one on yesterday's quiz first? On yesterday's quiz, you had this. You had this projectile. You had this problem where I threw something up in the air, and when you read the problem, it said he threw it up at 40 feet per second. So that was your initial velocity. I kind of gave you the equation, but you were supposed to put the 40 in right here. He also was at an initial height of 84 feet. So there was an 84 right here. This was Monday's quiz. You had a little word problem like this. And in the words it said, he's standing at an initial height of 84 feet and he threw it up at 40 feet per second. So, but I had sort of, anyway, so you were supposed to fill those in and you got this equation. Now, I don't know who, a lot of people did okay here, but do you understand that this is called the position or the height equation, or the position equation, and his derivative is what? I think a lot of people didn't catch this. This is a super important idea. His derivative is the velocity equation. His derivative is the velocity equation. I think a lot of people were trying to recall, oh, what's my old physics equation? Shit, I can't remember my old velocity. It's not. It is your old physics, but you don't have to remember it. It's the derivative of height is velocity, and that's an important calculus concept. The derivative of height is velocity. So here's the velocity equation. Later on at question C said, can you find the velocity? Find the velocity when t is 2. So what do? Plug a 2 into your velocity equation. Part A and B were a little tricky. Part A was, when does it hit the ground? So what do? When does it hit the ground? Yeah, that has nothing to do with the velocity. When does it hit the ground is just solving this. Right, you guys? Solving this quadratic. And so you should use the quadratic formula, I think. Some of you had, I don't know. You need the quadratic formula, I think, and you get this answer 3.86 seconds. I think I said you could round it to 3.9, but
Yeah.
Yeah, I got 3.9. You said there's 10.
yeah.
Yes, I got that right.
You guys okay? This is easy. Sort of. Yes, sir?
What if we did physics and still got the right answer?
Well, this is physics. That's a kind of a funny question. This is physics. This is the equation. No matter what class you're in, this is the equation for this ball, and this is the velocity of the ball at any moment. It's the slope of the tangent line or it's the velocity at any moment. Yeah, it's the instantaneous velocity at any moment. So hang on, what was part B? So you needed part A to get part B, because part A was when does it hit the ground, and part B was what was the velocity when it hits the ground. So the velocity at the ground was would be this velocity formula with this plugged in, right, you guys?
Right.
I mean, for parts B and C, you just needed this velocity formula. It's really good. Then you just plug in, for part B, you plug in 3.86. For part C, you plug in a 2. You could have done part C without even doing A and B, is part of my point here.
Right.
But you needed to do A in order to do B because you needed this time. You needed this time. Am I confusing you? Are you okay? All right. That was 2 separate questions. Am I confusing you? Are you okay? You said yes. All right, good. I don't know. So this is different. 11, you asked me to do 11. 11 is similar, but it's different. And 11, I think I should start writing down this equation again. Let me write this down. This is kind of always our equation for falling objects. What this problem says is that Alice was in Wonderland and a trap door opened and she fell. And she fell for 10 seconds before she hit the ground. What's a little weird about this problem is, you know, Alice is walking around here, right? See her? And then she hits this trap door and falls. I don't know, what you could get your brain all screwed up and pretend, you could think that this is the ground. And then she falls below the ground, and that'll trip me out, man. But anyway, can we just pretend that this is the ground? That's what I mean. Let's call this the ground. And so she fell from wherever she was through this trap door, and she fell and she hit the ground. So when she hits the ground, what do you know? It's called the ground. What do you know about the ground? S is 0. Good. The height is 0. So she hits the ground, and the height is 0, and guess how long it took her to get there? 10 seconds. Now, did we know her initial height? A lot of times, like in this problem, they gave me the 40 and they gave me the 84. Do we know her initial height? Did they say how high she was?
No, we have to find
No, in fact, that's what they asked for. So I don't know what this S naught is. It was not given, and in fact, that's what they're asking for. The initial height of the height of this fall. I do know it took her 10 seconds, though. Do I know her initial velocity? Do I know her initial velocity? Did somebody push her down? Did somebody throw her up first and then she fell through the hole? I think she just fell. She just stepped and fell. So I think her initial downward velocity was 0. See, the initial downward velocity of this is, when I just let it go, the initial velocity was 0. Of course, as soon as it leaves my hand, it's got some velocity. But initially, when you just let something go, its initial velocity is 0. But there's 3 scenarios. You let something go and its initial velocity is 0, or you throw it up and its initial velocity is positive, or you throw it down and its initial velocity is negative. I mean, there's 3 scenarios, but if you read this Alice problem, I would say her initial velocity is 0. Do you agree? Okay, then we're good. So what do I got? I got this height equation with this being 0, so it's negative 16t squared, but this is unknown. This S naught is unknown, which is the height of the room. But I know these 2 pieces of information. Look at these. Look at this. What can you do with this? Plug it in. Right. When t is 10, the height is 0. This height function is a 0 when t is 10. Can you find S naught?
You just have to multiply that.
It's 100 times 16, it's 1600. You move it over to the other side, it's 1600. Is S naught? Guess what? That's the height of the room. You guys with me? I mean, I'm sorry if it's too easy. See, I know it is easy. The math is easy. The math is easy. The words, reading the words, and is the hard part, I think. I mean, but I guess you get better at it. I mean, you got to read the words and turn the words into math. When you turn the words into math, like I kind of do, I don't know. There was nothing really difficult about this problem, really. But
you just pick out information.
yeah, right.
That's needed. Yeah.
Jot it down and figure out how you can use it.
Yeah.
It's all about this formula, kind of. So I think I just answered part A. What is the height of the room? You know, I might the word problem might have been a little confusing. Maybe I should have described it a little better. But hey, what was the velocity when she hit the floor? What's her velocity when she hits the floor? Well, then you don't. This equation. You need a velocity equation, which is the derivative of this, which is actually the derivative of this, which is
Negative 32.
32t plus. Okay, that's it.
That's it, because that's a number. Right, the derivative of this is negative 32t, and the derivative of this is 0, because it's a number. It's 1600 is what it is. But, so there's the velocity at any time. What do I want? The velocity when she hits the ground, which was 10 seconds. So this is also easy. So plug in 10 seconds. The velocity at 10 seconds is this, right? So I just made it. It just sounded weird and scary because it was Alice in Wonderland. I don't know. A lot of my problems are like that. I don't know. A lot of math problems are like that. You kind of, I don't know. Some of them require terrible calculations. Some of them just require a little insight, and the calculations aren't that bad.
Right.
But it's that insight that you need, kind of that. I don't know. The skills, the problem-solving skills, kind of. Any other good requests? Yeah, maybe. I'm kind of, you know what, I got an idea. I want to do, and maybe I need to do more of this, but I want to do this number 2. And there was one of these on your in-class quiz, kind of like this. And students didn't do well on here. You ready? Look. This almost looks exactly like is it exactly?
It is.
It was actually
It's
exact.
the exact question.
Actually, the one on the quiz had a minus sign right here. So on your in-class quiz, you had a minus sign. I don't know if that matters a whole lot, but on this one, but anyway. So all this is a derivative, but this is kind of a. Let me show you this. So first of all, it's a product rule. So if you didn't catch the product rule, you lost some points on yesterday's quiz. It's a product rule. That's the first thing you have to realize. And so here I go. The derivative is the derivative of the 3x. 3. And then I write the other guy down. When I write him down, I'm going to call him x squared plus 1 to the 1/2, because that's what he is. So that's just me writing him down. So here comes the product rule. The product rule would be plus. Now I'm going to write down the 3x. And now I'm going to take the derivative of this square root thing. So the derivative of the square root is 1/2 x squared plus 1 to the negative 1/2 times the chain rules. A lot of people forgot this little chain rule. The derivative inside here is 2x. So there you go. Good job. If you did that, that's good. But here's what I'm really interested in that a lot of people didn't get, and that's the cleanup of this.
Yeah.
I'm interested in y'all knowing how to clean this up. nicely and efficiently. And my suggestion in the past, I mean, maybe I haven't done too many of these, but my suggestion was you factor out that you have this x squared plus 1 to the half, and you have this x squared plus 1 to the negative a half. And so what you do is you factor out the one that's the lowest power. So you factor out the x squared plus 1 to the negative a half. Now that's my main thing I want to factor out. You could also factor out a 3.
Yeah, I did that.
So I could do that later, or I could do it now. What I'm trying to do is teach you this, so I'm focused on this. Let's just do this. All right, let's pull the 3 out too. All right.
Yeah. Hold it there.
Jesus, it's hard to make a decision. But the main thing I'm trying to teach you is how to do this. Now watch here, because you didn't seem to catch it Monday. Anyway, here we go. When you pull the 3 out of here, it's gone. When you pull the x squared plus 1 to the negative a half out of the x squared plus 1 to the positive a half, what you're left with is x squared plus 1 to the first.
Right.
And that's kind of how this always happens. If you practice 3 or 4 or 5 or 6 or 8 of these problems, this is the game that you play. Now, do you not understand that? Are you not convinced that this is what's left? Right here, this is x squared plus 1 to the first. If you don't understand me, how about you multiply it back through? If you multiply it back through, you would add exponents, and what would you get? You'd get this. So maybe now you're convinced. Let's move over here. What's nice about this is this is gone. This whole thing got factored out. The 3 got factored out. The 2's can cancel. So what's left over here? An x squared. That's the nice part of that factoring move, is what's left cleans up so nice. I'm really almost done. I would like you to finish though. Can you add this stuff up, please?
2x squared plus 1.
2x squared plus 1. That's what that is, right, you guys? There's a 3 out front, and I think I'll drop this down to the denominator and call it a square root of x squared plus 1. So I just helped you with, this was on your quiz, and this is what I expect. I want it cleaned up. Do you have any questions about that?
So, I'm trying to figure out how to get x squared.
Well, what's left over here? So what did we factor out? We factored this out, so it's gone. Is that okay?
We got it.
What else did I factor out? The 3. It's gone. See, I factored it out. So what's left over here? I canceled those 2's. I canceled the 2's. So x squared. That, yeah, the 2 little x's.
Is it okay just to leave it x squared plus 1 to the 1/2 power on the bottom?
Sure.
Okay.
So then that answer, how did you get there? 2x squared plus 1.
Well, see, even though I got parentheses on this, there's no power on it. Remember we said it was to the first?
Right.
So there's really no power on it. So you can add this x squared with this x squared and call it 2x squared
Okay.
plus 1. I mean, I'm just collecting like terms. That's a 2x squared plus 1. There's my 3.
Okay.
And this guy I can drop to the denominator. Here, let's just try another one. What's this one? Watch this one. Are you ready? I ain't scared. Are you scared? This is another one. It's just like it. Listen, I'm going to do one little rewrite move here. I'm going to take that 5x cubed. I'm going to rewrite this. This is 4x minus 3 to the 1/3. You guys with me? Because it's a cube root. All right, so that's the function. I want to do a derivative, and it's the same kind of deal. Kinda the same kind of deal. Here we go. The derivative is a product rule. And the derivative of the first, 15x squared. Write down the second guy, plus, write down the first guy, and now I want to do this guy's derivative. Okay, How do I do this guy's derivative?
1/3
1/3
times parentheses 4x minus 3 to the -2
negative 2/3. When you subtract 1
times 4
times the
4.
derivative inside, which
4.
is a 4. That's it. I mean, we did it. I mean, you know, you should get some credit for this because, god dang it, you did a product rule. Good job. You remembered the chain rule, and you deserve some credit for this. And you get some credit for this. But you have to clean it up. And so my suggestion on cleaning it up now is you factor out that common what? What do I factor out?
4x
The 4x minus 3
to the
to the -2/3. Let's not even mess with the 5. You could pull a 5. You could pull. Let's not mess with anything else. Let's just do one thing at a time. I'm factoring out a 4x minus 3 to the -2/3. What is left right here? Well, I think the 15x squared is left. What else is left?
4x minus 3.
To the first. A 4x minus 3 to the first. How do you know? If you multiply it back and add exponents, you get this.
Right.
It's always to the damn first. That's how it works usually. Maybe not always, but almost always. Let's move over here. What's left over here? The main thing is this is gone. That's factored out. So what's left? 20. Can I call 5 times 4 20x cubed over 3 or 20/3 x cubed? Is that okay with you? 20 over 3 x cubed. Cool. So it's cool how it works, man. I mean, because then what's left cleans up. I mean, and it cleans up nicely because this is to the first, you can distribute this and 60x cubed minus 45x squared. I just distributed that. Plus 20/3 x cubed. Okay, well, I can add these two dudes together. 200/3, is that what that is? I just added those dudes together. This is sitting out front. I'm pretty happy with this. I mean, I accept this. Because you did the main factoring. Is there more factoring you could do? Could you factor an x squared out? Yeah. Could you factor a 5 out? I think you could. I think you could factor a 5x squared out of here. But I won't grade you on that, but I will grade you on this. Anyway.
So there's no, the final answer is not in like a division, like kind of like number 2.
You could do that too.
You can?
I don't even care about that.
Okay.
See, what do I care about? Yeah, that's the other. Maybe that's the other hard part of this class. What does he care about? What does he? So I try to be clear, but I care about a lot of things. I care about correct, cool mathematics, but what I care about is cleaning this up with this smart factoring move. You know, whether we put him now in the denominator or not is not. That's not relevant to me. I mean, we all know that. I hope, but factoring that out to get it efficiently cleaned up is important to me. Yes.
On number 3, you
Yep.
factor out,
Yep.
and what's in the denominator is gx squared, so it's 3x squared minus 7.
Yeah.
How do you factor out 3x squared minus 7 to the -1/2, and then out of 3x squared minus 7? Does that make sense?
Yeah. You might be left with 3x squared minus 7 to the 3/2.
How did you find that out mathematically?
Well, how do you? So the way I like to do it is, if I factor this out, I play the game of what's left. So what needs to go here, so when you add it, you get this. Jesus. But, watch this. Hang on, watch this. If you factor out an x squared, can you tell me what's left? Okay, guess what? You know what you did? Here's what you did. You factored out an x squared. That sort of means like you divided out an x squared. And so that sort of means you took the 7 and subtracted the 2 to figure out what was left. You factor out the x squared.
I guess when the fractions come, my brain
Well, that I know. So, but that's why I'm doing this.
Okay.
You're subtracting. If you want to figure out what's left, whatever you factored out, you're subtracting that exponent from what the exponent that was there.
So in this case, if it's to the first power, you would change that to 2 over 2, and then subtract that from -1/2, which is 3/2.
Yeah.
Okay. All right, I understand it now.
Yep.
You just changed that into a fraction. Okay.
Yes.
Where'd you get the 200 over 3?
I added the 60 with the 20/3, and I did it quickly in my head. So I took 60 over 1, and I multiplied by 3 over 3, so I made it 180 thirds. 180 thirds plus the 20/3 is 200 thirds. Sorry. I added those fractions and got a quick common denominator in my head. Right. What else? Number 3. See, that's a lot like it, and I don't know. That's the one he was just asking me about. Let's see. What is this? 10x squared over 3x squared minus 7. So 10x squared over the square root of 3x squared minus 7. You know, you got two choices, you guys. You could do that. You know, you could rewrite that as 10x squared times 3x squared plus 7 or minus 7 to the -1/2, right? You see what I did?
Yeah.
I moved it up. Anyway, it's your choice. And by the way, this is a 10x squared over a 3x squared minus 7 to the 1/2. You know that. You know that. So I can either do this quotient rule or this product rule. I don't want to mix up the two ideas, though. I don't want to mix up those ideas. But I got that option. Do that product rule or do that quotient rule. And to me, it hardly matters. They're practically the same. But that is my option. Either way will work.
So what you did was, for the product, when you get that as a product rule, you took that that G term, you moved it up to the numerator.
Well, right. So I did, look, right. So I haven't done any calculus yet, right? This is all algebra so far.
Right.
This thing with a square root on it is written like this.
Right.
It's a quotient rule. As it sits, it's a quotient rule. If you move it up and call it this, which, you know that's believable, true algebra, then I can do a product rule instead. But
I think it's easier.
But I don't know. I don't think it matters. You guys can debate what's easier and what's not, but I don't think it matters. I'll do a quotient rule. You ready? So quotient rule. Derivative of the top. Right down the bottom. And by the way, let me say something. That doesn't mean move the bottom up. It means right down the bottom as it exists, which is like that. I didn't move it up, so I don't negate it. I just wrote down the bottom. The derivative of the top times the bottom minus right down the top. And take the derivative of the bottom. How do I do the derivative of the bottom? 1/2 3x squared minus 7 to the -1/2 times 6x. Right? All over the bottom square. And this square root, when it's squared, is just 3x squared minus 7. It's to the first. I'm gonna do that. It's to the first. Nobody ever does that. You don't need to do that. I squared it. There it is. You guys okay?
So it's not squared.
Well, hang on. It was a square root, and it got squared.
Oh, okay.
So it's not squared now.
Okay,
Right. It was a square root, and it got squared. So good. So there I go. I'm done. I did the quotient rule. So now I want to clean it up. And what's the most efficient, cool way to clean it up? All the cool people clean it up. like,
Or you took out like every factor out.
you do this cool factoring move. Right, again, here's what you have to see. A big mess minus another big mess. And that's a term minus another term, and those two terms have some stuff in common. And I don't care to find everything they have in common. What I really want is to factor out the 3x squared minus 7. And which one do I factor out? The one with the lowest power. So I could factor out a 3x squared minus 7 to the negative 1/2 if I wanted to, out of this numerator. Are you with me? I could also get an x out of there, couldn't I? I could also get a 10 out of there, I think. Maybe even a 20, to tell you the truth. But let's not do too much at once. Can we just do one damn thing at a time? Let's just do this one thing at a time. Okay. All right, so I'm pulling this out. So now tell me what's left right here. The 20x is left. And the 3x squared minus 7 is left to the first. To the first.
It's always the first.
If you multiplied it back, you would see that. If you subtracted exponents, if you took this 1/2 and subtracted the negative 1/2, you're left with a 1. You can think like that. What's left over here? This dude's gone. I'm so happy. And I'm left with, can I call this a 3 here? 3x, 30x cubed. I mean, it's so beautiful how that works. You factor that dude out. It is all over this, 3x squared minus 7 to the first. And the truth is, I think I'll drop him down here. If I drop him down here, he's to the 1/2. But I'll join it with this to the first, and I'll have... So my denominator, I'll just write 3x squared minus 7 to the 3/2. Are you okay with that? I dropped him down and it combined these terms. Right. My numerator should clean up beautifully. If I distribute this, I'll do it right here. 60x cubed minus 140x minus 30x cubed. So I can subtract those x cubes and get a 30x cubed minus 140x. I'm happy with that. I'm very happy with this. How are you guys doing? You want to do any more factoring? I mean, you're done, but you could, in the numerator, you could factor out a 10x, right? Just have it sitting out here, 10x. What would you have? 3x squared minus 14? I think I did that right. Did I do this right? I mean, it's a big, nasty quotient. Well, that's why it's on your take-home quiz. Of course, I just did it for you. But that ain't the point. Study how to do it. You know what I mean? I mean, study the process. Understand it. What else you want to do?
So what goes in the denominator in the 10x?
Yeah, no, this.
Okay.
I just get lazy. Right at the end, I get a little lazy. Leave it unfinished. That's terrible. I got all kinds of house projects that are like that. One little thing left unfinished. What else you want to do? Oh, you want to see your quizzes?
Yeah.
There wasn't any bonus points on this quiz. It was 25 points. Everything was 4 points each or something. I'm just going to hit end on this.